Okay, so in this final lecture, I want to spend most of the time talking still about quantum diamond models, but in the last section, I'll try and give you a bit of an overview for other approaches, and then I'll try and tie together the different things that I hope I've got across in the set of lectures as a whole. So as far as quantum diamond models are concerned, there are really two things that I want to talk about. So, as I emphasized yesterday, at this special point in the parameter space, the Roxar-Kivelson point, we can write down the ground state wave function exactly and explicitly as uniform amplitude superposition of all the dimer configurations. And one thing that we'd like to do on top of that is understand excitations. And I told you about one type of excitation in 2 dimensions called the Vizon, a kind of Z2 flux, in the last lecture. And what I want to start with in this lecture is how we can get an understanding of a different type of excitation which is related to photons in conventional quantum electrodynamics in ways that will become clear as this lecture progresses. So the first thing I want to say about quantum diamond models is to do with these excitations, and the second thing that I want to say about quantum diamond models is to do with understanding what happens as we go away from the special point where we can write down the ground state wave function, the RK point. Okay, so going in detail to this first topic of photons at the RK point, I think it's worth saying that there's actually a long history of doing the kind of thing that we're doing here, which is to try and write down a variational wave function for the excited states. And as far as I know, it goes back to work by Feynman in the early 50s on superfluid helium. And thinking about that problem, he said, first of all, that you can say some basic things about the ground state wave function if you think of it in coordinate space, because it's actually trivial to show that it must be nodeless, and so the only thing you have to think about is the amplitude, and that must somehow go to zero when hardcore particles come together, but otherwise be presumably as flat as possible to minimize kinetic energy. And then he said if you have some knowledge of the ground state wave function, you can construct excitations which, in that system, of course, Bogoliubov quasi-particles, phonon modes, basically by attaching phases to the ground state wave function which depend on the density fluctuations. So the idea, going back to quantum diamond models, is to build excitations based on density fluctuations in the dimer configuration. But of course, the dimers are close packed. It's not their density that fluctuates, it's only their orientation. So the idea is to make excitations which are based on density waves in the dimer orientation. So what we want to do is find some operator which we can use to act on the ground state wave function which we know to give us a trial wave function for the excited states, And because we've got a translationally invariant system, those excited states will be labeled by a wave vector. So to set up some notation, let's introduce an operator which simply tells us whether there's a dimer present on a bond or not. So we need a position label for the bond position. And I guess in principle, knowing exactly where the bond is located, it tells us its direction as well. But somehow it's going to be important to keep track of bonds oriented in the different directions in the lattice. So we can use a separate label for the bond orientation. And this thing is simply going to be +1 or -1 according to whether a dimer is present or absent. So to have an operator that tells us about waves in reciprocal space, we just Fourier transform this. And then our trial wave function will be what we get when we act on the ground state, which is this equal amplitude superposition at the RK point, with this operator that modulates the phase of different configurations according to how the dimers are oriented. And then in the spirit of the variational approximation, what we need, well, I say variational, but of course we haven't actually got any variational parameters in this wave function. It's just a one-shot approach. What we want is the expectation in this state of the Hamiltonian minus the ground state energy, and the ground state energy, of course, is trivially 0, but I'll write it in for explicitness. Now, if we just stare at that expectation value by itself, it's perhaps not terribly easy how to proceed. But what does help is to think about what's inside the ground state expectation in terms of commutators. Sorry, I should have said that we want to divide all this by the wave function normalization in case that depends on these operators sigma. So if we think about commutators, if we look at a nested commutator like that and expand it, then of course we get two terms with H in the middle and two terms with H either first or last. And clearly this very first term corresponds to one of the pieces that we want to calculate, and the second term is pretty much the same, except that the conjugate is swapped around, but the effect of the conjugate on this operator is to change the sign of the momentum, and since we have inversion symmetry in the lattices we're thinking about, this will give us the same as that. And then we have two terms with opposite signs to the first two, with Hamiltonian appearing either last or first, which means that when we think of plugging these into an expectation value like this, the Hamiltonian will act on the ground state and generate this ground state energy. So, in other words, we've got two terms which give us that, and two terms which give us that. So, what we can say is that from the variational principle, the difference in energy between the lowest excitation at wave vector q and the ground state energy is bounded below by a numerator which will be the expectation of this commutator and a denominator which will just be the normalization. Okay, so how might that be useful? Well, we'll be particularly interested in low-lying modes, and especially we'll be interested in modes whose energy goes to zero at some places in the Briand zone. And looking at this formula, we have a chance for that to happen if f goes to zero. Provided the denominator doesn't go to zero at the same point. Yeah.
Just f going to zero faster than the circle effect.
Yes. Yes. And this approach, as well as being one that Feynman used for liquid helium, was also very useful in the context of the fractional quantum Hall effect. Okay, so thinking about our problem of quantum dimer models, if we're looking for the possibility that this numerator goes to zero, obviously the easiest way for that to happen is if these commutators vanish. So what we really want to think about is when the Hamiltonian might commute with this operator that's creating the density waves. Well, of course, you remember that the Hamiltonian has these two terms in it, the potential term and the kinetic term. The potential term doesn't move dimers around, so it will commute with this density operator. So really the question is whether the kinetic term can commute with the density operator. And the point is that if we think about a particular plaquette in the lattice, which, say, has dimers on it originally and some components of the wave function, then if the kinetic term acts on this, it'll flip the dimers into the other configuration. And, yeah.
Why do you have inequality there?
Well, it's a variational principle, so that this is some variational approximation to an excited state with wave vector q, and if I made a better approximation, then I might be able to get a lower bound on the excitation energy.
So what is E of Q?
Well, it's supposed to be the true minimum energy excitation at wave vector q. Thank you. Yes. Sorry. Thanks. Okay, so thinking about this commutator, according to whether the Hamiltonian acts before or after the spin operator, we'll be applying the spin density operator, the dimer density operator, either to that configuration or that configuration. And to get this commutator to be zero, we require these two things, these two configurations, to make the same contribution to sigma tau of q. And I kept this label for the dimer orientations in for completeness, but let's now fix a particular direction. So let's take this direction tau to be the x direction. So that means that this combination of dimers will make a contribution here, and this combination would make the opposite contribution because these two dimers are absent. So if these things are going to wind up being the same, we need to pick our wave vector so that the term that comes from this dimer cancels the term from that dimer, and that means that we need we get the commutator to vanish if the wave vector is pi, or at least, yes, yeah, pi. In 2D or in 3D. Okay, so then you can go further and look at how the commutator varies away from zero as you go away from this corner of the Briand zone. And what you find is that if we write Q is this special point plus some wave vector k, then you find that f of q is proportional to either just ky squared in 2D or kx squared plus ky squared in 3D. Yeah.
Can you say again when you say Q goes to pi pi?
So the point is that these once we've fixed tau equals x, we're looking at the occupation of the horizontal bonds. And so since these horizontal bonds are occupied in this configuration but not in that one, they make a contribution here but not here. And since you want these two things to be the same, you need to find some way to cancel the contribution of this dimer against the contribution of that dimer. And if you take the y component of q to be pi, then this dimer comes with the phase factors from e to the I q dot r cancel between these two. So at that stage, it looks as if you might have soft modes along lines in reciprocal space. So the line kx equals 0 here, sorry, this should be ky squared plus kz squared, or the line kx equals 0. But to know whether we actually have soft modes or not, we have to think about what happens to the denominator. So in other words, we have to think about the ground state expectation of this dimer correlator. And that's something that we can get from things that I talked about in the context of spin ice in 3 dimensions, or the height model in 2 dimensions. So it'll turn out that this has zeros too. So if we look at this ground state expectation, well, if we're asking about occupation of dimers on the bonds in this direction, then if you think of that mapping to fluxes in 3 dimensions, the occupation of these bonds by dimers is related to the emergent gauge field. And if we're looking at bonds in this orientation, then it's the x component of the emergent gauge field. And so this is going to be proportional to an average over classical dimer configurations, but that's something that we described with the statistical weight that involved the exponential of b squared. And then this is going to be the average of bx, bx. And then there's one thing which I've left out, which is the wave vector arguments here. And if you think about the details of how we related dimer configurations to these effective fluxes, then it involved firstly introducing the sublattice labels and then defining orientation direction convention for the bonds, say from sublattice A to sublattice B. So when we compute the flux, this dimer contributes an opposite amount to that dimer, and that means that if we're looking at dimer correlations at a wave vector q, then the flux correlations are at a wave vector k. So this is a correlator between fluxes at wave vectors k and minus k. Okay, now in the lecture on spin ice, when I talked about correlators for this effective emergent gauge field, I gave you a result in real space. Now we need the result in reciprocal space. But it turns out, and I'll say quickly why this is reasonable in a moment, it turns out that this is delta ij. Well, in general, we might think not just about the x components, but arbitrary components. And this is proportional to delta ij k squared minus ki kj over k squared. So why is that reasonable? Well, firstly, we don't have any gradient terms here, so we expect something which is, in terms of power counting, k to the power 0 in the correlator, which clearly this is. And secondly, we have div b equals 0, and in reciprocal space, of course, that means k dot b equals 0. So k dotted with the correlator should also be equal to 0. And if you dot k into this correlator, then you can convince yourself that you get you do indeed get 0. So if we use this result in here, what we're looking for is just the x components. So we take these labels I and j, both equal to x. So in the numerator, we've got k squared minus kx squared. So this is ky squared, ky squared plus kz squared over k squared. And this is all for 3D. And we could have done the same calculation in 2D using the height model, and then we'd have got simply ky squared over k squared. So what this gives us for the dispersion relation the ky squared plus kz squared cancels between the top and the bottom, and what we get is something that's just proportional to k squared. In other words, we have an excitation whose energy vanishes quadratically as we go to the zone corner, but we don't have any soft modes on lines because away from that point in the zone corner, this estimate of the energy is finite.
So what do we call a photon if it's quadratically dispersed?
Right, that's my next point. So it's not like a photon, obviously, since it doesn't have a linear dispersion. And compared with a linear dispersion, you might say this is soft. But that will turn out to be, as I'm about to argue, a special feature of the Roxar-Kilfelson point. And if we go away from the Roxar-Kilfelson point, and if we're in 3 dimensions, so that we don't simply immediately go into an ordered phase of the quantum diamond model, then it turns out we get back to a linear dispersion. Okay, so any other questions on that argument? So what I want now is a framework which will allow us to talk about what happens when we go away from the Roxar-Kivelson point. So what we need is some continuum description. In other words, we'd like to write down an imaginary time action for the quantum problem that's in the same spirit as the statistical weights that I had for the classical problem, which is here for the 3-dimensional case, or in the 2-dimensional case was simply the height model. So let's start with 2 + 1 dimensions. And there are reasonably solid ways of deriving this at the Roxar-Kivelson point, but I'm going to jump over those and just write something down and argue that it's plausible. Well, firstly, the new thing that we need in a quantum problem compared to the classical one is obviously a time derivative, and the standard kind of thing to write down would be something quadratic like that. But then if we're thinking in terms of the dispersion relation that we've got, if we go into frequency space, this would give us an omega squared, but if the energy goes like k squared, then that means we'd better have a spatial term which goes like k to the 4th, or going back to direct space, it means that we need del squared h all squared with some coefficient which I'll take to be capital K squared. So that looks a bit surprising. Let's just think about what the consequences would be. So it's a quadratic theory, so we can easily work things out. And for instance, if we look at the fluctuations in the height field, then they'll go like 1 over omega squared plus k squared wave vector squared. Sorry, maybe k wasn't a good choice, but it's to tie up with things later on. It's meant to be capital K. Thank you. Okay, so as a check, we can think about the equal time correlation function. So this we get by integrating over omega. And if we do the omega integral, then from this we get something that goes like 1 over this stiffness times k squared. And that is what we had from the height model. And we know that the equal time correlations in the Roxar-Kivelson wave function are the ones of the classical dimer model, which is represented by the height model. So this is the result that we expected to find. Okay, but now if we look at this action, we realize that it's fine-tuned because normally you'd expect to find lower order gradient terms, so what's missing is a term involving simply grad h all squared. So one term that we can have is some coefficient rho 2 times grad h squared. And then if you think back to when I talked about height models, the fact that the height field microscopically is integer valued means that we can have cosine terms as well. Depending on the stiffness, these might or might not be relevant. Okay, so the special thing about the Roxar-Kivelson point is that this lowest order gradient term in the height field is missing. So that means that we can expect that the coefficient of that term should vanish at the Roxar-Kivelson point and more generally should go like 1 minus v over t. So if you think of the phase diagram, then I had a staggered phase to the right of the Roxar-Kivelson point. Well, when v over t is bigger than 1, this coefficient will be negative. So the system wants to have gradient in the height field, and if it's a uniform gradient, then this del squared term doesn't give any energy penalty. And so we can see straight away that we expect to have maximum gradient in the height field as soon as this coefficient is negative. And maximum gradient that corresponds precisely to the staggered dimer configurations if you think about how those staggered dimer configurations translate back into heights or into fluxes. Yep. Yes. And then on the other hand, when you go to V less than T, then it turns out that this locking term becomes relevant, and so you go immediately into a locked phase of the height field, which is a phase of the dimers with long-range order. So that way you see in 2 dimensions that the Roxar-Kivelson point is a phase transition between 2 ordered phases, and although we have deconfined excitations, the fact that they're deconfined is a property of the critical point rather than a property of the phase. So what's left is to look at the same arguments in 3+1 dimensions. So then we want to write our action in terms of the vector potential, which represents this divergence-free field. So the kinetic term looks like that, and by the same arguments, to get a mode with energy that's quadratic in wave vector, we need simply that term at the RK point. And more generally, we can have a term ρ2 times b squared with, again, ρ2 proportional to 1 minus b on t. So, again, to the right of the Roxar-Kivelson point, where this coefficient is negative, we can see that the system wants maximum flux through it, which is the staggered phase. But now, if we're to the left of the Roxar-Kivelson point, then in 3+1 dimensions, it turns out that the extra terms, including this and also cosine terms in A, that you might add to that action, are all irrelevant. So you can just focus on the lowest order terms. Well, we've got this term b squared, and now this term we can think about representing in a different way. So if we just remember that in general, in electromagnetism, an electric field is the time derivative of the vector potential minus the space derivative of the scalar potential. Well, in our problem, we haven't really got a scalar potential, but if you work in the Coulomb gauge and you have no free charges, then in fact this vanishes anyway. So more generally we can think of writing that as the electric field squared. And we have an action that looks like the one for electrodynamics. And so we expect there to be excitations like the photon excitation with a linear dispersion relation. So we can expect excitations with omega proportional to k to the left of the Roxar-Kivelson point. So
what protects our hate point from becoming crossover distribution?
I think it's probably, I'm not absolutely sure about this, but I think it's probably a rather strange transition that has a kind of mixed character. I mean, it's true that the phases either side are completely unrelated because you go immediately into a maximum tilted state, but there isn't a jump in the derivative of the ground state energy in the way that there would be at a first order transition. Because the energy density of the staggered phase only varies linearly with the distance away from the Roxar-Kivelson point.
But are there terms that we can introduce, like symmetry with
I think in 3+1 dimensions, these terms are the only ones that you need to discuss that transition. Well, I guess you need something microscopic to limit the maximum flux.
So what happens to the curl of B and the action on the right?
Right, okay, so at the Roxar-Kivelson point, this is the lowest term in B, and we know that from the form of the dispersion relation, but if we go to the left of the Roxar-Kivelson point, then we have this term which is lower order in derivatives, and when this is present, then that's irrelevant, so I dropped it. Okay, so we have this analog with electromagnetism, and there's one more brief point which I want to make, although I won't have time to go into any details. So in 2 dimensions, yesterday I told you about creating a different kind of trial wave function for excitations that instead of being extended waves were point-like. That was the Vizon, and I described all of that in 2D. We can make similar trial wave functions for point-like excitations in 3D at the RK point. and they turn out to be electric charges. In this language. And of course the magnetic charges are simply the monopoles that I talked about in the framework of spin ice. Okay, so with that I want to move away from quantum diamond models and just spend a few minutes trying to sketch some of what I haven't really had time to tell you about. So really I want to talk about two directions. One is numerics for quantum systems, and the other is slave particle approaches. So, of course, there's a range of numerical methods. So one is quantum Monte Carlo. If we start with frustrated spin models, then generically we get a sign problem, which makes it hard to go to low temperatures. So this is really only useful if there's no sign problem. And one of the good things about quantum diamond models is that they can be studied that way, and so you can get unbiased and reliable information about the phase diagrams and so on. The other approach that's becoming useful in 2D, although originally it was developed for one-dimensional systems, is DMRG. And so you apply it to study 2 dimensions by studying long strips. And as I'll mention at the end, there are systems where that's given us results which now seem pretty definitive. Okay, so if you set out to look at other analytical approaches beyond thinking about quantum diamond models and starting from the Roxar-Givelson point, then an important direction is to think of the spins as being made up out of underlying particles, and those particles might be fermions, which of course is reasonably enough since the spins are there because of electrons in the first place, but you can also represent spins using bosons, and let me talk briefly about both of these. So if we use bosons, then at least the starting point is to think about the Schwinger boson representation of spin operators. So for SU2, we have 2 species of bosons, and we represent the Z component of spin in terms of the difference in the numbers of particles of each species at a given site. And then the raising operator, for example, converts particles of one type to particles of the other. And the important thing is that we have a constraint if we want to represent spins of a certain length, which of course is on the range of values for Sz, and we can implement that by fixing the total number of particles of the two species to be I guess it's 2s. I forget whether it's 2s or s. Maybe it's s. Okay, so at that level, that's simply a way of rewriting spin operators in terms of bosons. And when we start doing calculations, we can think of implementing the constraint via a gauge field. Which then has a chance of becoming the emergent gauge field in the spin liquids. Okay, so then to actually do calculations, you need some way to control things. And the general approach is to take some kind of large N limit. So the simplest possibility is to go from SU2 spins to SUN. Which means, in terms of this boson representation, that instead of just having two species, you end up with n species. And that was something that was developed by Arovas and Auerbach. But then for technical reasons, to represent frustrated magnets, or that's to say magnets on non-bipartite lattices, it turns out that you need a different kind of large N limit, and rather than SUN, you need to take SPN, which coincides with SU2 at n equals 2, but is a different extension to larger N. And all of that was done by Reed and Sachdev in 89 or 1990. And actually, a lot of what also comes out of quantum diamond models comes out from this large N limit. Perhaps at the time, the worry might have been that one had wandered too far from the original problem, but of course it's reassuring to see the same physics coming from different approaches.
What's SPN?
Well, it's, UN conserves, it's SPN leaves a matrix like that invariant if you do rotations. It's with this block of ones and minus ones.
Why don't you also use SPN for bipartite lattices?
I think you can use SPN for bipartite lattices. It's that you can't use SUN for non-bipartite lattices. Okay, so one approach to slave particle calculations is to go to bosons and have this large N limit. Another possibility is to think of your spins as being made up out of fermions, which after all they are. So at each site you have fermion creation operators for up and down spins, and then you think of the spin operator in terms of these fermion operators and the Pauli matrices in the usual way. And now we have a constraint as well, which is that if we want to represent a Mott insulator, then we need to have single occupancy. And again, that's likely to take us to a gauge field. So if you think about pushing ahead with this approach, then obviously what you'll need to be able to do is represent some exchange terms in terms of fermions. And since the spins are bilinear in the fermions, something that's bilinear in the spins goes to a 4 fermion term. And if you take this Hamiltonian with 4 fermion terms on the bonds and make a mean field decoupling, then you get to quadratic fermion Hamiltonian, which has some sort of generic form with hopping terms and, in general, some pairing terms. And what you can try and do now is think about these parameters in the mean field Hamiltonian as variational parameters for a wave function. So what should that wave function be? Well, if you simply have this mean field Hamiltonian and take its ground state, that will give you a Slater determinant. But that by itself is not much good as a description of a magnet, because it has charge fluctuations in it. So what we need to do is project out the fluctuations by imposing this constraint, which we can do by multiplying by a factor like that. So then we have a projected ground state and now the thing to do is to choose the values of these variational parameters, minimizing the expectation of the Hamiltonian in that projected ground state, which you can do via a Monte Carlo calculation. In terms of understanding, this approach actually has some quite nice features. And one of those features is that it gives us a good way of thinking about the excitations. So clearly this mean field Hamiltonian has excitations, and if we're including these pairing terms, then we'd think of those as Bogoliubov quasiparticles. So we can run this whole procedure with a Slater determinant that's not just the ground state of this mean field Hamiltonian, but instead contains some Bogoliubov excitations. And those translate to the spin-ons that we were talking about in terms of monomers in the quantum dimer model. And you can also think of making other kinds of variations away from the ground state instead of taking the hopping terms to minimize the ground state energy. You could put some phases in so that you have fluxes around fluxes piercing some plaquettes in the system. And those correspond to Vizon excitations in the quantum dimer model language. And having this set of mean field ground states, according to the details of the model and the parameters that you choose, means that you can see possibilities for spin liquids that you can describe through this approach. So as the fermions hop around the lattice, they may pick up phases from these hopping matrix elements, and so they see fluxes, and those fluxes might either all be simply pi fluxes, in which case you'd say you had a Z2 gauge theory, or they might be general phases, in which case you'd have a U1 theory, or they might also involve spin rotations, in which case you'd have an SU2 theory. And when you look at the bands for the fermions, then there are, again, various possibilities. So the fermions might, in the simplest case, be gapped. So there would be a gap for these spin-on excitations, or they might have a Dirac spectrum, or they might have a full Fermi surface. So you can imagine that there might be spin liquids of these various types with different sorts of gauge fields and different properties for the spin-on excitations. And then, in general, as you go to the right in this listing, things become less stable. If we start with Z2 fluxes and gapped excitations, then we have a theory that's certainly stable, but when we have more low energy degrees of freedom, then we have more ways in which it can become unstable. So.
So how does spin order show up in the ground state of the Slade fermion approach?
Yeah, so do you mean, suppose the system that we were studying was not a spin liquid, but some ordinary nail state? Well, then, to describe it, you'd have additional variational parameters which would polarize the spin directions on different sites, so that so that this slated determinant would already have Néel order in it. Well, I think within this description, the spin-ons, I mean, within the projected mean field description, the spin-ons are bound to be deconfined, just because the excitations of this mean field Hamiltonian are. So then you have to study it beyond mean field theory, yeah. Which is precisely the question about the stability. Okay, so just to finish, I'd like to try and write down in a couple of sentences the sort of main themes of these lectures and summarize some of the things that we definitely know. So the first point was that frustration at the classical level gives you degeneracy and also strong correlations, the kind of thing that we described with the emergent gauge field or the height model. And as we saw with the example of monopoles in spin ice, already at the classical level, you get, or you can get, deconfined, fractionalized excitations. And then when you go to quantum models, we have, at least from looking at quantum dimer models, several possible phases which are identified. So we have the possibility of a gapped spin liquid with Z2 gauge theory, and the excitations then are spin-ons and bosons. And we have several examples of that. So in 2D, we have the triangular lattice quantum dimer model. And from DMRG, I think it's reasonably clear now that the spinor half Heisenberg model on the Kagame lattice is an example of the same kind of phase. And possibly the simplest example, in fact, although I haven't talked about it, is the toric code. And you can have examples in 3D as well. When we go to 3D, we have an additional possibility, which is the U1 spin liquid, which I've been talking about in the first part of the lecture with photons and so on. So that has magnetic and electric monopoles. And also these gapless photon excitations. And of course the magnetic monopoles are the monomers which correspond to these spin-ons. And one example of this is the diamond lattice quantum dimer model, where pretty reliable simulations have been done. And another place where it's found is thinking about hardcore bosons. Hopping on the pyrochlore lattice. So I haven't really said anything about the background to that, but I mention it now because at least potentially this is something that you could hope to realize with cold atoms, whereas the quantum dimer model itself is obviously a bit further from an experimental realization. Okay, so unless there are questions, I'll stop there and we can have lunch.